So, hello everyone. Thank you very much for joining us the fifth UFMRM webinar. And today we are very happy to have Dr. Sanita Vetra-Carvalho to give us a talk about their project they're using the CCTV image to improve the flood forecast. And the talk will be about 20 minutes, and we will have the discussion at the end of the presentation. And now the floor is yours, Sanita, please.
Okay, thank you, Albert, and thank you for inviting me to give this talk. So yes, today I'm going to talk on the project that I'm involved currently, which is called DARE, and how we sort of part of the project is interested in using the CCTV images to improve the urban flood forecasts. And first of all, I'd like to introduce the whole team of the DARE project. So we have Sarah Dance, who's the project leader, and I am working together with Javier Garcia-Pintado, who's in University of Bremen, and David Mason here in Reading as well. So this sort of, set of people work on urban flooding aspects using the data assimilation. Then there's another part of the project that involves Stu Grimmond and Joe Waller, and as instrumental scientists, and they are working on sort of understanding urban weather errors and urban weather aspects on the errors. Then there's Onno Bokov involved from Leeds and a PDRA2B that's going to work with him also on urban flooding. And then lastly, there's also Institute of Environmental Analytics involved, and they're going to be, so John Blower is going to sort of work along with David Mason to implement professional software for SAR delineation algorithm that is going to be developed, and David's developing as part of this project. And then there's other sort of partners for the project, so Flood Forecasting Center, Environmental Agency, CH2M, Met Office, London Climate Change Partnership, Environmental Agency also. So there's sort of a lot of different diverse set of people involved working on this project to bring it all together. Okay, so why worry about urban flooding? I mean, we all have seen our cities grow considerably over the last few decades, and by 2050, it is predicted that 64% of the developing world and 86% of the developed world will be urbanized. And further, the United Nations have also recently projected that nearly all of the global population growth from this year to 2030 will be absorbed by our cities. So, I mean, that means that already complex cities are going to become even larger, denser populated in the near future, which only means more buildings, more infrastructure, more complex structures, more social behaviors, complex social behaviors. And also, then at the same time, climate change effect means that our cities and towns will face more frequent Okay, yes. So due to the climate change, it means that our cities and towns will face more frequent floods due to rising sea levels and also more frequent and intense rainfalls. So this combination then means that any flooding in urban areas is going to have a greater effect on human life, both socially and financially. So what can we do about it? And there's many different ways people are tackling this, such as making cities greener, implementing appropriate defenses, improving flood forecasting for the cities. And we have seen in previous series doing this through improved flood forecasting models for the urban areas. And there is sort of in this last section, we're working on trying to improve the flood forecast for the cities, but rather than improving the models directly or working with such, we're tackling this from a data assimilation side. So the aims of their project are to improve the urban flood predictions through the data assimilation. And in cities, we're doing this through the novel and standard observations of urban floods. And another part I mentioned is to produce an algorithm and a working code for SAR delineation in urban areas, and to understand error structures of urban weather observations. And finally, a big part of this project is also to network and to achieve goals through collaboration between various fields and people involved in urban flooding. So part of my work in this project, and also what this talk is going to be, is on improving the urban flood predictions through the data assimilation, using the various observations. And I always welcome any sort of comments and suggestions, and a possibility of working together with anyone else involved in urban flooding, interested in data assimilation aspect of it. So the DARE project is funded by EPSRC Senior Fellowship in Digital Technology for Living with Environmental Change, and it's a senior fellowship that's held by Sarah Dance. Okay, so first of all, what is data assimilation? So we can think of data assimilation as a bridge between a model forecast and all possible observations of the state. So it isn't a bridge in a sense that it's linking the two pieces of information, but it also can be thought in a sense that you are balancing the two pieces of information as well, depending on how much you believe in one or the other at any given time or point. And the reason for doing data assimilation is because all models have errors, and inundation models have a number of error sources, such as inflow errors, bathymetry parameters, model errors, and so forth. And also, we do not have high resolution observations of every state, at every point in the state space and time. And observations also have various errors associated with them. So by combining these two pieces of information, in a data assimilation, what we can achieve is a better forecast for the state. So how does data assimilation work sort of in a mathematical sense? So we have the model on one hand. So here we have the model that takes the current state variable vector at the current time, advects it forwards in the time, and we have associated error with this state. So at the next time step, this is our model state. And we sort of denoted that it's got nx variables in this state. So the error we have to describe in some sort of way, and we have to have some knowledge, at least roughly, of how the model error would behave. Then on the other hand, we have observations of the system, and we denote them by y. And here, usually the y is much smaller. So the size of the observations, the number of observations we have, is usually smaller than what our state size is. And we also have associated observation error, and we sort of, distribute it along with the covariance matrix R. And then we can map between these two spaces using something called observation operator, which is denoted by H here. So we can take a state variable and we can map it on to observations. So say satellite observations or a radar or any direct sort of observation measurements. And then we can combine these model and this model information and observations as follows. So here we can think of F stands for a forecast. So this is something that model is giving us at this current time. Y are our observations, and we have our observation operator mapping our current state onto observation space, so we can directly compare what our model thinks in observation space to what actually we have observed. And then this produces our analysis vector of what we had originally predicted, and includes our information we have obtained from the observations. And equally, we can update our error forecasts as well, not just the state, but P here stands for model sort of forecast. Ensemble, you could also think if you're using an ensemble. And K here is the Kalman gain matrix, which basically is a matrix that balances the errors that we prescribed that were in these matrices Q and P and R. And it's so in P here and in R, and it balances the errors between our what our forecast errors in P and our observation errors in R. So in case if we, for example, would have a very good belief in our observations and we have very small observational error, we would put more value onto observations than on our model forecast. Or likewise, if our observations were, we didn't think they're very accurate, we'd have a big observational error, and then there would be more value given to the model forecast, and only very little contribution would go from the observations towards the analysis. So these equations are known as the Kalman filter equations, and all ensemble data assimilation methods are based on these equations. And for the ensemble methods, you would approximate this equation 5 to be able to implement it numerically. And there's various ways of doing that depending on the ensemble method you're really using. And there's other various data assimilation methods that are popular, and these include variational methods such as 3D VAR or 4D VAR, particle filters there also, and there's a growing list of sort of different hybrid forms between ensemble and variational methods, or particle filters and ensemble methods, and so forth, that can be found in the literature as well. So it's sort of schematically, this means that we have observations and a model state, and these two are inputs for our data assimilation. We assimilate observations into the model state, we update it, and so we can only, we can as well as updating a state, we can also update the parameters, depending on what sort of thing we're after, for the data assimilation to improve. And then our updated state goes again back into the model. It's forecasted until the next time we have observations, and we repeat all the cycle. Okay, so why would we use the data assimilation in urban flooding apart from sort of the direct of improving the forecast? Other reasons we could use it is because it also improves the forecast uncertainty, so forecast errors. We would have better understanding of those. We can use data assimilation to learn more about the model and improve model and understand more of a model error. We also can use data assimilation to assess observation networks, and if any additional observations would have a desired impact on our analysis. And we can estimate uncertain model parameters and inputs. Also, such, for example, in flood forecasting, bathymetry parameters, input flow, and so on. So in this talk, I will talk more sort of on using data assimilation to produce more accurate flood forecasts, and also use data assimilation to estimate and improve our understanding of model parameters and input data. Okay, so what kind of urban observations are there available of floods? So we have river gauges. These are sparse in space, but they are frequent in time. We have SAR satellite images, which are both frequent in time and space and have good resolution in both dimensions. However, there are some issues in urban areas with these, which I'll touch on a little bit later. There's CCTV cameras, which have varied spatial distribution depending on location and how many of them are. However, they are very frequent in time, so they offer a good source of information if they are in the correct locations, near rivers in a sense. There's river cameras, which are sparse in space, but again, frequent in time. There are some cities have surface water road sensors, but these are on very few cities where this is available. And then there's other crowdsourced data, such as Twitter data, where sort of information can be found on floods. So let me kind of give you an example of what has been done using SAR images, assimilating SAR images in Tewkesbury. And this has been work done by Javier and David Mason and Sarah and from the project as well prior to the start of the project. So this was work done with list flood model on near Tewkesbury for the rivers Avon and Severn. And so the inflow boundary conditions is an ensemble from hydrological model. The domain was 30 by 50 kilometers at 75 meter resolution. There was various tributaries that contributed to the basin, and then so assimilation was done by assimilating water level observations from 7 Cosmos Skymed overpasses SAR images in November 2012. And on the left, you can see an image of the whole domain where you can see the cities and the rivers that sort of contributed in the domain. These are the 7 observations from the SAR image, starting on 11th of November, sorry, on the 27th of November 2012. And then the last one is on 4th of December 2012. And you can see how the water heights have been extracted in these images. Okay, so this shows how the data assimilation has worked for this example. In a gray, we have ensemble members predicting of what water height would be at this Worcester station. In red is the ensemble mean. And here we have a line on the top here horizontally, which says what was the bank height at that particular location. Dashed lines show the satellite overpasses, so the 7 images that I showed in a previous slide. This is the time when they were assimilated in the data assimilation domain. And the blue one is the gauge. Is the gauge station observations, which were not used in this assimilation run. So what you can see is that every time there was an observation, data assimilation has brought the mean and ensemble, so it's brought the states closer to what was observed actually at this point. And there were a number of ensembles which were predicting that the river would be going out of the banks at this point, just before we have the first, sort of starting from here to here, there's a lot of members predicting that the river would go out of banks, and the mean sort of goes just here. You know, if seeing that forecast, you'd think that actually there's a very high chance that the river will be going out of the banks, where in actual reality, it came close to that, but it never really went out of the bank. So data assimilation has improved in this case, what we predicted, and there's a great benefit of using the data assimilation and the SAR images in this situation. So from these sort of two investigations, we have seen that SAR images are positive. Assimilating SAR images has a positive effect and improves our forecasts. It also improved uncertainties of uncertain parameters, and it stabilized ensemble-based covariances in this situation. However, there is some issues in using SAR images in urban areas, and this is mainly due to the building shadows and backscattering, which would mean that only certain parts of SAR images would be usable for in urban areas for the assimilation. So we in their project are interested in using CCTV images to sort of supplement the SAR data that is going to be available, of cities as well. So an idea is to use both the traffic cameras, so CCTV images that you can see here of London on 2nd of June this year, and also using river cameras on the rivers that is available, which has more sort of direct link to the river and the water, to supplement the images, the SAR images, for assimilation in the cities. Okay, so CCTV observations are available in all major cities. So this is an image on the map in London. And in London, there's just over 900 CCTV cameras available in the entire London area. And other cities that we're interested in the UK are Bristol, Glasgow, Exeter, Leeds, Newcastle, Tewkesbury, and also Reading. Council has few CCTV cameras around in Reading where we are. So we're looking to use all of these available cameras and to record images in these cameras when there is a potential of a flooding in any given area. So currently we have run and downloaded some data for London, and these are the images from London that we have obtained. So 2nd of June, you can see in this sort of circle-like area, there's on part of the North Circular, there was surface flooding after heavy rainfall and thunderstorm, and that had slowed down the traffic, and the warnings were issued of surface flooding in the area and slow traffic. We have captured some heavy rain currently as well, and also some beautiful sunrises over London. But as yet, we haven't sort of got any flooding, as in river flooding going out of the banks images in London currently yet. So we are at the beginning, and we are now combining the code and trying to make one unified code for all the interested areas, so we could download directly for all areas where flood forecasts are predicted, and we could run this for the whole UK, for all the cities that we're interested. After we've still set few of the cities, we still need some information for accessing the cameras, but it's all work in progress. And so once we completed the observation network, we are interested in testing our data assimilation system with the CCTV observations in some simplified environment initially, using list flood hydrological model. We also eventually are interested in setting up the data assimilation system with an urban hydrological model, and seeing, what sort of analysis we can do with that and improvements, as well as using the new SAR algorithm as well in urban areas. So we have quite a lot to do, and till the end years to go, which is good. And you can sort of keep up. We got a blog that we keep putting all the latest information and of what we've done and looked and found or are interested. Here's the link. And and also sort of if you're interested in data assimilation, we have our own system in Reading called Empire that's been developed in Reading. It's open software, so you can download it and use it. And it's basically a data assimilation system that's based on MPI calls that can be easily connected to any given dynamical model. So if you're interested, you can have a look there. And another project I worked before on, which was SANGOMA. And so if you're interested in data assimilation, you can find on this site also free code for data assimilation, going from diagnostic tools to analysis methods, perturbations, utilities and transformations, and the code is in MATLAB and Fortran. So that's just for the information in case you'd like to use parts of the data assimilation for any of your work. And these are the references for the work that was presented here today. That's it. Thank you.
Okay, thank you very much, Sanita. I would like to invite the audience if you have any question for Sanita. If not, can I begin the first one, and then maybe
Sure.
people will jump in. Just interesting about it's very interesting that you talk about this kind of assimilation. Just wondering for this CCTV image, you have the spare location and sparse location of the observations. So how will this data assimilation model cope with this kind of discontinuity in terms of space?
Well, I mean, so an important part of the data assimilation is to provide these covariance matrices, both for the observations and both for the observations and for the model. And so this would be, through the observation errors, you could put in sort of how to smooth this information when you assimilate it.
Yes.
So it would be sort of, a jump and spike in one place.
Yes, but for example, if you have some certain change in this urban environment, you have some road, terrain, topography change. So how will this affect your estimation of errors or?
Well, you mean, so if in one point suddenly there would be a high, high adjustment coming from the data assimilation?
Will that affect the result? Because, yeah.
But I mean, I think this is so, all this smoothing sort of is done through the covariances. And I mean, also another idea is to go and use smoothers. So that's part actually of the thing that we'd like to look if using ensemble smoothers would help as well of distributing the information. But going through the covariances is one of the ways of ensuring that, we don't have a sudden jump in one side, in one particular location, that the information is smoothed out.
Okay. Do we have other questions from audience? Can I ask another one? So how this assimilation how frequent you are going to do this kind of assimilation? Because you have very frequent observation from CCTV camera. Yeah. So would you do that kind of assimilation by every 5 minutes during the simulation, or how would you deal with this kind of temporal resolution?
Well, I mean, so that's, yes, I mean, I haven't thought in huge detail of that, but I mean, that would also depend very much on the model that you're using. It would not be very, depending on the model time step. So you couldn't obviously assimilate more frequently than what the model time step is. You could combine the observations and then use them in one set, but I'm not sure if that would be the most advisable. Or you could use an average of the, what you observed in a certain time period from your observations. But no, I mean, that's an important question and something that I need to think about more in detail before, we start using it.
Yeah.
But I mean, currently the observations from SAR images are sort of, once in 12 hours, once a day.
Yeah.
So we're hoping that, with this we can assimilate more frequently, but not on a 5-minute intervals.
Okay. Do we have any questions? Katja, please.
Hi, thanks a lot for the interesting talk. I have a question. So we're studying here impacts of flooding on road transportation. And there are many dimensions of it which hasn't been studied really well. And I'm wondering how we can use the CCTV images to draw any conclusions of drivers' behavior when they approach flooded road. So you said that you haven't found too much flooding since you started looking into it, but do you think this can be seen anywhere?
What you mean seeing what the driver behavior near the flooding, sort of?
Yes. Yes.
Yes, I mean, I think, we haven't found anything yet, being that we've only started, recording in London in the last 2 months, sort of thing. So, the image that I showed of surface flooding in the North Circular is sort of the most flooded currently we have got in London. But yes, I mean, you definitely could see, of how the traffic is slowing down, and by spending some time on observing London traffic through the CCTV, which is available to everybody, you could see how the rain affects and how it slows down people in the rain or in the flooded areas as well. I would think so.
Sounds great. Thanks.
You're welcome.
If there's more question?
Can I ask a question?
Yes, please, Dave.
If you have a person who's got a mobile phone and takes a picture at some location which is tagged, but the orientation of the phone isn't known, how can you extract a water level, say, from that flooded image in order to assimilate the water level into the hydrological model?
Yes, that's a good question. So, I mean, if you know, so from most of the images, you would know when you say it's tagged, so you'd know the actual location, but you could use the digital terrain maps or, sort of similar to know what the, surrounding area in that location is. And then there's Google Maps, and on most city points are all Google mapped, and you could visually also see on which point this camera was looking, and roughly, how high it would be and at what angle, I would imagine. I guess that would be my thinking.
You've got a problem of how to georegister the image from the camera to the British National Grid.
Sorry, say that again.
Well, the camera the image is going to come at some arbitrary angle, although you know the position and roughly the height. You've got to work out we've got to work out what angle it is looking at in the BNG coordinate system.
Yeah, I mean, I guess that's so, you know, I mean, that would be in my kind of thinking, you know, visually, that would be something that you could see from any of the Google Maps as to what, you know, are the features in that image. So you would know which way it's looking, but that's something human, obviously human interaction as to diagnosing in which way that person was pointing when they took the image.
Yeah, okay. Perhaps you could use area correlation of the image you got from the mobile phone and the LiDAR British National Grid coordinate system image.
Oh, I see. Yes. Okay. Yeah.
Just,
okay, that's a good idea. Yes, that's a good idea. Thank you.
Just follow up this question. So, are you going to implement some kind of image recognition algorithm?
So initially not. Initially, we're going to do this sort of, you know, by hand. But yes, I mean, it would be nice that it would be possible. And I have seen some algorithms of how to extract water heights from cameras.
Mm-hmm.
So yeah, I mean, that would be something that I'd like to do in the near future.
Good. Any more questions? If not, I would like to thank Sanita for your presentation. It's very interesting, and I would like to thank to audience for your time for attending this webinar. And we will have the next webinar short in 1 month's time, so it will be announced on our usual social media channels, and you will receive the notification, and hopefully I will see you on our next webinar. Thank you very much. Thank you.
Thank you, Albert. Thank you very much, everyone.
Thank you, Sanita. Very interesting talk.
Thank you.
Thank you.